Hi, I'm Kai. Now I'm going to do the question 10 of homework 8 for probability and stochastic processes. For question 10, we need to show that if the normal process is y-sense stationary, then it is strict sense stationary. At first we can let x of t, we can let the process s of t is normal process and y-sense stationary, and then if we want to prove it is strict sense stationary, then we want to show the density function fx of x1, x2, and so on up to xn, t1, t2, and so on up to tn is equal to fx of x1, x2, and so on up to xn, t1 plus epsilon, t2 plus epsilon, and so on up to tn plus epsilon for any n, any t1, t2, and so on up to tn, and any epsilon. First, we know x of t is normal, so we can write down its density function fx of x1, x2 up to xn, t1, t2, and so on up to tn is equal to 1 divided by the square root of 2 pi to the power of n times the determinant of matrix C times e to the power of -1/2 times x minus eta transpose and times C inverse and times x minus eta. And C is the expected value of x minus eta times x minus eta transpose. And then we can rewrite these two terms as the vector form. So the x minus eta we can rewrite as x of t1 minus e of x of t1, and so on up to x of tn minus e of x of tn. So for this term, the transpose term, we can rewrite as the row vector. So the dot product of these two vector will be a matrix. We want to compute this matrix. So we can see the first element of the matrix, which is this term times this term. So it will be the expected value of x of t1 minus e of x of t1 square. So it is equal to the variance. So the variance is equal to the expected value of x of t1 times x of t1, which is the expected value of the x square times eta square, which is the expected value, the square of the expected value. We know x of t is a y-sense stationary, so the expected value of x of t is a constant eta square. So the first term will be the autocorrelation, and x of t is y-sense stationary, so it will be r of 0 minus eta square. So we can use the same method to compute the C matrix. So the first element of the matrix will be R of 0 minus eta squared, and the last element of the first row will be R of T1 minus T and minus eta squared, and the first element of the last row will be R of T1 minus Tn minus eta squared, and the last element of the last row will be R of Tn minus Tn minus n squared. And so we can know C depends on T1 minus T2 and T1 minus T3 and so on, up to Tn minus 1 minus Tn. So we can rewrite it as C of Ti minus Tj for any I is not equal to j, and ij is equal to 1, 2, and so on up to n. So now we can rewrite our density function. Fx of x1, x2, and so on up to xn, t1, t2, and so on up to tn as the fx of x1, x2, and so on up to tn, ti minus tj. For I is not equal to j, ij is equal to 1, 2, and so on, and the density function. So this density function f of x, x1, x2, and so on equal to xn, t1 plus epsilon, t2 plus epsilon, and so on up to tn plus epsilon. This density function also depends on ti plus epsilon minus tj times epsilon. So this term is actually ti minus tj. So we can see that this density function is equal to fx of x1, x2, and so on up to xn, t1, t2, and so on up to tn. So we prove that the normal process x of t is y-sense stationary, then it is strict sense stationary.